This is part 2 in our series on population ecology. When we left our story, we had been talking about how populations grow and how we can model that mathematically. We saw that we can have an exponential growth curve if we just consider the intrinsic rate of growth, looking at the birth rate minus the death rate, and not considering any other factors such as the limiting factors, such as limited food or space or the accumulation of waste over time that could limit how fast a population can grow. We designated carrying capacity as K, and we reformulated our equation to say that the growth of a population is the R max, the intrinsic rate of growth, multiplied by the population size, but then adjusted by this factor of carrying capacity and what fraction we were towards reaching carrying capacity, where K minus N shows us the difference between what the potential of the population of the environment is to the population and where we are towards reaching that, and then dividing it by the whole. We said that if the population is very small, then this factor is near 1, and therefore the population grows near its max rate. But however, as the population nears the carrying capacity, then this factor would near 0, and our growth would near 0, which gives us, instead of an exponential growth curve, a logistic growth curve, or this S-shaped curve. So this is how populations grow. They'll grow slowly at first, and then accelerate, and at some point when N gets starting to get closer, high enough level to so that this factor starts becoming important, away from 1 and closer to 0, we'll get this inflection point where we start to decrease the rate of the growth of the population, and eventually we'll get to a growth rate of 0. Now, in real populations, it tends to look more like this, where as we reach carrying capacity, we often overshoot that number, and we get into this stage where we're above carrying capacity. And this is not necessarily a happy time for a population, because there may be starvation going on or disease running rampant through the population as the density is too much for the environment. And then we get this drop off in population due to deaths, the death rate being higher than the birth rate, when we'd actually go below carrying capacity, and then we could start to grow again, and you can see that would start to kind of vacillate around this number as we reached a population that was in a steady state, had reached its capacity for that environment. So in logistic growth, a population at low density starts growing slowly, and then it accelerates until it levels off at the carrying capacity, and there's our formula we used. Now, we can describe populations as being R-selected or K-selected. An R-selected population, remembering that R stands for the intrinsic rate of growth, birth rate minus death rate. In R-selected populations, where population size is far from K, so that density-dependent factors, the factors that are dependent on how many people are in the area, are not playing a very large role in selection. These populations are sometimes called opportunistic, and their growth rate is near the R max. We contrast that with K-selected populations. These are populations whose size is near the carrying capacity, so that density-dependent factors play a very large role in selection. By selection, we mean how well an organism can cope and survive in its environment. Those individuals that are well suited to handle and compete in these high-density situations are selected for, and those that can't are selected against. And in a R-selected population, individuals that are very good at maximizing their rate of growth, these opportunistic organisms, are selected for. Now, there's a term in here that I want to focus in on, and that's density-dependent factor. And we need to kind of compare and contrast that to density-independent factors and how they can control the growth of a population. So let's define these terms. Density-dependent controls is when that high density and overcrowding put individuals at a greater risk of dying. For example, due to predators, as the population grows, each individual's the predators can come in and easily pick off the prey. but also parasites and pathogens are easily transferred from individual to individual much more easily in a very dense population than a spread out population. And this actually carries a lot of concern for human populations, as human populations are moving from a more rural setting where they're spread out to urban centers and cities where a pathogen can spread easily throughout a population. Density independent factors are those factors which can decrease a population regardless of the population's size. An example would be natural disasters. Thinking about these issues makes me wonder about what happens to our population as we reach the carrying capacity. Or a better question, what is the carrying capacity of Earth? How many human beings can the Earth sustain indefinitely before density dependent factors start making it so we aren't growing anymore, where disease and famine and shortages of food and space start to impact how well we can grow? Let's look at these graphs. Let's start with this one. This is a graph showing the world population growth throughout history. See if we can zoom in on this. And you can see that throughout history, the human population has been following a exponential growth, which really just took off in this area here, and we'll zoom in on this area in a minute. You can see the effect of the Black Death. But for very long periods of time, human populations was growing, but growing at a slow, steady rate, and then it just took off. Now, some of this taking off is just the mathematical reality of an exponential curve, but also think about the improvements in healthcare and food production that kind of coincided with the already growing base population that we're building off of. But the question is, can this rate of growth be sustained? We know that when we look at other populations in population ecology, that we say that the answer is no. Eventually we have to reach some point where this is going to have to level off. Let's look at this graph. It's a little frightening. In fact, it's scaled differently than the other one, but it's showing from 1800 to 2000 and let's see, we're in here. This was made in 2006, but it was projecting forward to 2039. It looks like here. And you can see how much this rate is accelerating in terms of billions of people and the number of increasing per day. It's kind of a scary idea. Now, the question is, have we, or one of the interesting ideas to think about is how we as humans have maybe taken this ceiling, the carrying capacity, the point at which this should level off, and maybe raise the ceiling, where the improvements in agriculture and the improvements in medicine and healthcare have actually taken our carrying capacity, and keep moving it out further and further into the distance, so that as the population increases, we've made the Earth able to sustain more people through technology and healthcare and food production. At some point we have to ask the question if we have a responsibility to start to slow this growth down intentionally through things like family planning. And we know that there are certain governments around the world that do encourage a very specific number of children being raised, and give incentives to have less growth in terms of population. The question is, what's the impact besides just the running out of space and food and the threat of famine and disease? What does it mean from an economic development standpoint? Let's look at something called an age structure chart. This is one of our concepts in demographics that we need to look at. What this kind of graph shows us is, for each age level, you see the ages in the middle here, 0 to 4, 5 to 9, and so forth, how many males and females, or how much of the population is made of that age group, and then also shows you the male versus female percentage of that population. And the interesting thing to see is that a population like this one that's fast growing, the issue is not so much now, but what does this mean in the future? Because as this bottom part moves up and moves into the reproductive time of their lives, they're going to produce even more, and the base of this pyramid could get bigger and bigger and bigger. And then we see an age structure like the United States, where we have a much slower growth, and then an age structure graph, a chart for a country like Sweden, which is showing a zero growth, where at each age level there's approximately the same number of people, obviously less at the very top because the death rate is high. and not that many people can make it to that age group. Now, from an economy standpoint, a country like Mexico has to look at this and say, well, where is the economic development that's going to provide jobs for this base population down here, this young population, as they move up in age and become part of the working population. So often, population ecology is tied into the study of economics. Let's look at one last concept before we finish up with our population ecology, and that's the idea of survivorship curves, and looking at different types of organisms and kind of the pattern at which they survive. So here we have three different types of animals: a human, a squirrel, and an oyster. And if we all start with 1,000 of them being produced, how many of them survive? And not only how many survive, but in what pattern do they survive? Well, for the oysters, you can see that in the first few years, or percentage of their lifespan, many of them, or most of them, don't make it. They are food for other organisms. But at some point, if you get past a certain point, you're going to survive to a very large percentage of your maximum lifespan. But so not so many of the numbers survive for a very long time, but those that make it will stay a long time. Contrast that to a type 1 survivorship curve, which we see in human beings, where early, a large percent of the humans survive through half their lifespan, and of course, as we get older, eventually we get to 100% of our lifespan, and therefore we could have 0 people. But this type of curve is very common in animals that show a lot of parental care. In reality, we probably should draw this with a little bit of a dip at the beginning and then leveling out, because the first, at birth, we do lose. It's a very vulnerable time, and so we have a little drop off there. But once you kind of get through that first rough patch, that vulnerable patch, you tend to survive until age-related things finally get you. But then you contrast that to a squirrel, and what this is basically saying, a type 2 survivorship curve, is that, hey, any day of your life, you're just as likely to die as any other. And we'll stop there, and we'll let that be our previews or reviews, however you're going to use them, for population ecology. Certainly during class, we'll talk about some of these concepts in greater detail and make sure we answer any questions you have. As you've watched this video and hopefully the prior one, bring questions to class. Be prepared to discuss them and answer some questions based on the concepts that you've seen.